So once the Big Bang theory had been established, the big question remained, what then is the fate of the universe? What's going to happen? Will it be bound? In other words, will there be enough gravity to snap it back? Or will it be unbound and expand forever? The key to knowing this was to knowing the critical density of the universe. Is there enough stuff out there to provide enough gravity to bring the universe down, to halt the expansion and to even snap it back? They had a great name for this, the idea that the universe might get crunched back together, the big crunch. And then if it expands forever, you might call that the big chill. So, what about this critical density? Most astronomers now believe we have an answer to this question of whether the universe will snap back or expand forever. But when I first started teaching astronomy, this was really one of the big major questions. So let's take a look at what we know about the critical density. Now, the critical density is represented by that symbol there, omega naught in this case. Omega naught, the critical density of the universe. If it is less than 1, it means there's not enough stuff out there to stop the expansion. It expands forever. If, however, there is enough stuff out there, enough gravity, then the universe should snap back and contract. What do we find? Well, when we add up all the galaxies that we can see, here's what we get. 0.01. Something in that neighborhood. Far, far short of the mass needed to bring bring the universe back together in a big crunch. But what about dark matter? We know that actually there's much more dark matter than there is the regular matter that we can see. But guess what? Even with dark matter included, you see that you only get to about 0.2 or 0.3 for omega naught, still far short of snapping the universe back. As you can see there, it's amazing how much dark matter there is out there. We'll talk more about that in a little bit. But this doesn't even include the fact of what I think is really maybe the greatest discovery of my students' lifetime, the greatest scientific discovery, and I think the greatest scientific discovery since I've been teaching astronomy. And it all happened around 1998 when some astronomers were studying distant supernovae, type 1 supernovae, and they were trying to measure how much the universe is slowing down. Right, because the universe has been expanding, gravity's trying to pull it back together. Now remember, gravity gets weaker with distance, with increased distance. So as the universe is getting larger and larger, gravity is sort of losing its chance to snap it back. And they wanted to know how much, though, gravity was at least slowing down the expansion. Even if it wouldn't snap it back, how much is it slowing down? And guess what they found? It's actually speeding up. This was wild. I mean, this made no sense whatsoever. I even told my classes at the time that this couldn't be right. The chances were that they would find out soon that their observations were incorrect. Because there's no force out there to do this. Gravity doesn't work that way. Gravity should bring things together. This didn't make any sense at all. Well, it's 2015, and nobody yet has proved their observations to be faulty. So I think I might have to give up and concede that they were correct, that the universe seems to be speeding up. But again, what can be doing that? What is out there overpowering gravity? Well, they've come up with a new name for it. We'll get to that in a second. First, I'm sorry, let me talk about this great chart here showing the history of the universe. If you think of the whole universe, let's pretend that the Big Bang here on the left started on January 1st, and we'll call today December 31st on this cosmic year. And at the very beginning of the year, in the first few seconds of the year, I guess you could say, you had the Big Bang and you had what we call inflation. The universe had to inflate at an incredible amount, faster than the speed of light, to give us the universe we see today. And right after that, maybe a few minutes into the new year, is when you have a low enough density and you have the formation of atoms that allows radiation to fly freely. And that's when we get that baby picture of the universe that we see from WMAP and from COBE. Now, you notice right after that, for the first sort of couple weeks of the year, maybe through mid-January, there are no stars in the universe. the dark ages of the universe. There are no stars. And then after 400 million years, or maybe a couple weeks on this calendar, you start getting the first stars. And throughout January and February and March, galaxies clump together. So you have the first galaxies forming, including the Milky Way, probably sometime around March. And then for billions of years, look at this, the universe expands at a fairly constant rate. Eventually, our sun and Earth, our solar system forms. But in the last few billion years, look at this. Interestingly enough, that's showing the way it flares outward there, both at the top and the bottom, shows this acceleration that the universe is starting to speed up. We just don't know why. So they've come up with this great term for it, dark energy. At this point, they might as well call it magic, because we really don't know anything about this. We are really pretty clueless about this dark energy. And it may turn out that maybe we're wrong in some other way. Maybe our physics is wrong. I don't know what's going to happen with this. But right now, it appears that as space expands, that this is a property of space itself. Something in the vacuum of space itself. The vacuum pressure is there, forcing space apart. And the larger space gets, the more spread out the universe is, the more noticeable the effects of this dark energy, if it exists, the more noticeable the effect is. So that's those are sort of the only clues that we have. In a funny way, you could say this actually brings back what was called the cosmological constant. Let me tell you a story about this very quickly. Albert Einstein's equations in 1915 with general relativity showed that the universe should be either expanding or contracting. But when he went to astronomers to ask him which it was, they told him, no, the universe is static. And the great Einstein, instead of sort of believing in the courage of his convictions and believing the math, he goes back and he stops the universe. Why? How? He just puts in a new term he calls the cosmological constant. He makes it up out of thin air to stop the universe. And then about 15 years later, when Edwin Hubble proposes that the universe is expanding, well, Einstein felt kind of foolish. He realized it was there all along, right in front of him. He called it his greatest blunder. But he might get a chuckle out of the fact that essentially we're bringing back a cosmological constant today. Except this time, instead of to stop the universe, we're putting it in there to speed up, to accelerate the universe. And we may look very foolish on this as well in the near future. Who knows? I don't know how this one's going to play out. Here's what we know so far about the universe, the things we actually know. Right now, it appears that dark energy just dominates the universe. It represents 65% of the universe, the matter and energy of the universe. Dark matter, which is we're not totally clueless on, but we're at least somewhat clueless on that represents 31%. If you do the math, everything that we understand, all the stuff that we can see and do experiments with and understand represents a whopping 4% of the universe. That's kind of embarrassing when we have to admit that we don't understand 96% of the universe. That's one thing that we know. We're kind of aware of our ignorance. Now, we have done a great job in the last 15 years or so really narrowing down the age of the universe. They even tweaked it a little bit. It was 13.7. They've raised it to 13.8 billion years old. And we can feel pretty confident about that. That's when the Big Bang occurred. That's pretty awesome, actually. They did a great job with that. Why does that number make sense? Well, we know that globular clusters are about 12 billion years old at the oldest. There was a time when they thought the universe might only be 10 billion years old, and that didn't make any sense. You can't have stars older than your universe. So this number, it fits very well with the oldest known stars. And it fits in perfectly with what we now know about the universe accelerating. So 13.8, they're feeling very good about that in terms of the age of the universe. Now, I'd mentioned inflation, that the universe had to expand incredibly rapidly, faster than light, actually. Well, that was all proposed by Alan Guth and a couple others around 1980 or so. That's what it takes to give us the picture of the universe that we see today. If you had this super fast rate of expansion. Now, last year there was quite a bit of buzz when it appeared that we had proof finally that this really did occur. And the proof was this: just like radiation got spread out as the universe expanded, in this early inflation, gravity waves themselves would have been stretched out during the inflation. And it appeared last year that they found the imprint of these waves hidden in the cosmic microwave background. It was a big, big deal last year in 2014. Well, maybe not so fast. Here's what it's supposed to supposedly look like. Now they're actually starting to debate this. So I don't want to talk too much about this because this could actually just be wrong. Their observation may have been wrong in this case. It's going to take further study to find out. Thanks for listening.